So work, energy and power we are going to do. Work, energy and power concept is very important for you, because understanding the concept of work energy theorem, conservation of energy, conservative force, non-conservative force, it is included in all chapters of class 11 after work energy power, after this chapter, as well as in class 12 understanding electricity magnetism will be proper with the good concept of this topic, work, energy and power. Although power is not very important for understanding those chapters, but concept of work and energy, work energy theorem, conservation of energy required page by page. So let us start the concept of work first. We are not going to define, we are going to start from an expression of class 9 or 10 physics, what we have learned. That is the expression for kinetic energy. Kinetic energy of a particle is given by half mv square. You know, kinetic energy of a particle is given by half mv square. Mass of the particle is m and its velocity is equal to v. Now, if a body is in motion, an object is in motion, a particle is in motion, then it has kinetic energy. We will say that kinetic energy of a boy who is running is more than kinetic energy of a boy who is just walking, isn't it? And by the time we state about energy also, the boy who is running is more energetic. Normally we say that more energetic than the boy who is running slowly. Now, kinetic energy of an object is given by this. This can be seen as this expression also, half mv dot mv. It means half p dot v. You can write this way also. P stands for what? P stands for momentum of the particle. All these things are related. We will be discussing all these one by one. But remember, when we are writing that P and V in this manner, then it is quite obvious that P and V have the same direction. Okay? P stands for what? P stands for momentum and V is the velocity. So kinetic energy we can express in this manner also. But this is for single particle. For a system of particles, what is the kinetic energy? For a system of particles, kinetic energy will be kinetic energy of the particle 1 plus kinetic energy of particle 2. We assume that this has n particles of masses m1, m2, mn, and they are moving with velocities vector. If the velocities of the particles are v1, v2, vn respectively, then this is going to be half m1 v1 square, half m2 v2 square, plus half mn Vn square. We can write this as half sigma mi Vi square. This is total kinetic energy for a system of particles. Now, this kinetic energy can be changed. How to change the kinetic energy? An object is in motion, this object. This is moving with some velocity, say u. Object has mass m. We apply a force over there. That force is F. By the application of force F, after some time you can see that velocity is changed to V. Okay? So there is a change of kinetic energy. This is kinetic energy initially. This is half mu square. Kinetic energy we can state state 2 or finally half mv square. To change the kinetic energy, to bring it more kinetic energy in the object, we need to apply a force. If force is not applied, there will be no change in kinetic energy. Isn't it? You need to apply force over there. If you apply force, then kinetic energy going to be changed. But the question is, in what direction the force has to be applied? See, this is our common experience only, that if we apply the force in perpendicular direction, the object does not move. If we apply a force this manner on this object, no displacement. I mean, no change in K. To change K, to change the kinetic energy of an object, a tangential force is required. If you say that no, I apply the force here, okay, it's fine, you are applying in the direction. So what I am going to tell you, you have to get a component of force along the direction of motion of the object. Then only you can bring a change in its kinetic energy. So to change the kinetic energy of an object, we need some force in the direction of motion. If the force is not directed that manner, I mean, if it is moving, say, towards right, if the force doesn't exist in that direction, then at least you need a component. Okay? So to move the object in forward direction, a force is required which has component this way. That will refer as tangential force, Ft. You can apply it here also, no problem. But if we go by component wise, then this force, F normal, is a no work force that we have done before. This is no work force. So this displacement of the object is due to this tangential force. Okay, tangential force is required. If the force is not tangential, a component will take it along the direction of motion where it is intended to move. Now, this kinetic energy expression, if we take kinetic energy equal to K, take Ke equal to K, then K is half mv square, you know. Let us differentiate this expression with respect to t. What do I get? dk by dt equal to half m d dt of v square. This is half m 2v into dv by dt. Alright. So this is going to be like this, half get cancelled, m dv by dt, m dv by dt is force, and that force multiplied by velocity. This force is tangential force. We take it as Ft into V. So the change of kinetic energy, for change of kinetic energy, dk by dt stands for what? Change of k. For change of k, we need to apply a force. Without force, you cannot change the velocity, and this Ft, I told you, it is the tangential component. Ft stands for tangential component of the velocity. You have to think here about this expression. Rate of change of velocity going to be Ft into V. So force is responsible, and you can write by using the vector here that if we write now dk by dt, we try to write this manner, that Ft into V. Ft is what? The tangential component I told you, that is f cos theta into V. Okay? That V is what? You write the expression for V here. This is f cos theta into dr by dt, because V stands for rate of change of displacement. So this is nothing but dr by dt. So if we remove dt from both sides, we can write dk as f dr cos theta. This can be written as f dot dr. Okay? So change of kinetic energy is f dot dr. You got a new term here that will be defining as work done. Okay? This f dot dr is called work done by the force F to displace an object by the distance dr. Okay? So you can get an expression here that dk equal to w. W stands for f dot dr. Now if you want to calculate this w equal to f dot dr, because there is a differential term on right side, I tend to write this one as dw. dw will be f dot dr. Now if you are going to calculate net work done, will be what? Net work done will be w, that is integration of f dot dr. This is nothing but integration of f cos theta into dr. But this expression stands for change of kinetic energy. Now w, if you say that dk equal to dw, then if you integrate this expression from k1 to k2, this integration going to be from w1 to w2. So k2 minus k1 is nothing but w2 minus w1. Okay? So we can write this as K2 minus K1. So work done on the whole path is change of kinetic energy. Okay, this is called work energy theorem. Okay, some points need to be discussed. This will refer as work energy theorem. Work energy theorem. But what about this force? Is this force only one force? Is this force sum of many forces? Is this force conservative, non-conservative? Is this force external? Is this force internal? All these things should be clarified here. You must try to know it. So, work energy theorem statement, let me write first. Work done on a body, equal to change in its kinetic energy. But this work is done by net force, done by the, you can say, resultant force. Let us try to understand. Actually, this resultant force means sum of all the forces. So, if we take, let F equal to F1 plus F2 plus F3 and so on. Okay, these individual forces, this F stands for what? F stands for resultant force. F stands for resultant force. F1, F2, F3, Fn, these are all individual forces. So what expression do you get? W equal to F1 plus F2 plus F3 plus this way Fn dot dr. Okay, this is going to be equal to F1 dot dr plus F2 dot dr plus this way Fn dot dr. Okay, so this is actually work done by force F1, this is work done by force F2, so work done by force Fn. So can I state that therefore work done by, and this work done stands for what? That we have seen. This is equal to K2 minus K1, final energy minus initial energy. Work done by the resultant force is equal to change of kinetic energy. This is applicable for all system of particles. Any system of particles has to obey this. But concept of resultant force involve what? This force may be force external. This force may be F internal. This force may be non-conservative. The force may be conservative one. Basically, in this chapter, we will be discussing in terms of these four forces. Example, you can ask me, what are the examples? Why you are telling all these external force? External force means the muscular force I am going to apply. Internal force means this we can refer as muscular force applied. Any form of muscular force you are applying on it, that is F external. F internal force is what? It may be electrical, it may be gravitational, okay, because electric force acts between two charged particles, gravitational force acts between two masses, non-conservative force. Already we have studied friction here. This is force of friction. Conservative force may be a force where net work done 0. A force, I'll do in details about it. A force whose net work done in a round trip is equal to 0. That is conservative force. Non-conservative force we can define that manner, but all those we will be doing in details, don't worry, it will be done. So work done by resultant force is change of kinetic energy, and what kind of forces act over there, that I have explained. We are going to work on this, but before that, this is introductory session on work, energy and power. I have related kinetic energy with work. This is the most important concept here that is introduced here. Now I told you power, basic idea you will get in this session. What is power? Power means that rate of doing work. Power P, what you have understood, power P is rate of doing work. So this power P is going to be dW by dt, isn't it? But W, what we have seen? W, we have written this manner. W or dW, whatever you say, dW. dW is what? F dot dr. We have just done, put it there. So it is d dt of F dot dr. This we can write as, therefore P equal to, now what? Will you think both F and dr are variable quantities over there? Let us assume, let F be constant. Let F be a constant. Okay, if it is not constant, then we will discuss in calculation part. Here you assume that F be constant, then F will be free of derivative. It is going to be dr by dt, so this will be F dot v. So power developed or delivered, power delivered on an object is measured by this. Unit of work you have already done in junior classes, that I haven't told you. Power, I think you have done that also. Work done unit of W normally done in joules or erg. 1 joule equal to 10 to the power 7 erg. That you know. Power is what? Unit of P is joule per second or watt. Okay? Power delivered to an object, section of particles, whatever you say, that will be 1 watt if the rate of doing work is 1 joule. Clear? Now, we'll be discussing some problems on work done first before we go to the next section of this discussion. We'll be discussing more on calculation of work. How to calculate work done? This work done formula we already got. Net work done is, and this F stands for net resultant force, F dot dr. Okay. Now this work done formula, if we apply for a force like this, just take one numerical example here. Number 1, calculate work done by the force F equal to 3I minus 2j plus k to displace an object from A 3, 1, 2 to B 2 minus 1, 4. We are going to calculate this work done. Work done by the force F to displace an object from A this to this. This work done is very easy to calculate. We will be answering it here. That F dot dr you first find. What is dr here? Here dr going to be what? That AB vector. AB vector is what? Position vector of B minus position vector of A. That is 2I minus j 4k. Force is not variable here. Force is constant. If the force is constant, then what to do? Then we will write, then we will say that the expression is F integration of F dr cos theta. Okay? But I don't want to take it in this form because the question I have asked in terms of vector. Here force is 3-dimensional. Displacement of the object also 3-dimensional. So work done will be accordingly. Position vector of B minus position vector of A. 3I plus j plus 2k. So dr vector is going to be, dr or AB vector is going to be minus I minus 2j plus 2k. This is dr. So work done will be what? dw will be what? dw will be F dot dr. This is 3I. We did not integrate here, nothing is variable. So this dot minus 2j plus 2k. Okay. So here it will be minus 3 plus 4 plus 2. That is 3 joules. So work done in this case going to be 3 joules. This is the simplest application of the formula you got. That dw equal to F dr. We need not integrate, that's why. Now, if I ask you the question this manner, find the work done by the following forces. F1 is I plus j plus 2k. F2 is say 3I plus j minus 4k to displace an object from A001 to B314. I haven't told you these forces are conservative, non-conservative, internal or external. So how do you solve this kind of sum here? Here we need to find the net force, resultant force. So resultant force F is given by this F1 plus F2. Add these two, it is going to be 4I, this is J, sorry. Resultant force 4I plus 2J minus 2K. AB vector, position vector of B minus position vector of A, this is going to be 3I plus J plus 3K. This is AB vector. Okay. Now work done will be what? F dot dW, in this form if you write F dot AB. You take the dot product of these two vectors, it will be 12 to minus 6, that is 8 joules. Okay. Hope you have understood when many forces operate. I mean F1, F2, F3, F4. Every time you find the resultant force. And that resultant force, I am repeating the concept again, it is work done, it is change of kinetic energy. This is our work energy theorem. Clear? Hope you have understood with those examples. Now, this work done expression, if I write once more that W equal to F dot dr or dW is F dr cos theta. Suppose that theta, this is applied force, makes some angle theta with the horizontal. We have taken the component. Just let me explain the situation. This force applied F, this F makes an angle theta. Component this way F cos theta is responsible for the displacement. Now this theta may be from 0 to 180 degree, sorry 0 to 90 degree. In that case work done will be positive. So if theta remain acute 0 and just before 90 degree or 90 degree, then work done will be positive. But if theta goes from say 90 degree to 180 degree, then work done will be negative. But this concept of positive and negative force we can discuss easily if we consider the motion of object in one dimension. Object is going in one dimensional motion. So if the object goes from A to B, then work done by the application of force, tangential force, whatever you say, then work done is positive. But if it happens that we are applying force in this manner on a spring, we are applying a force this manner. The spring has some force constant K. Force will be developed against the compression, that is minus Kx. Here, work done by you. You are applying a force. You are applying a force. That force will be equal to this Kx. So, work done is what? Work done by the external force will be what? F into, if we write dx, this expression, and then we integrate for the elongation x, f dx, it will be 0 to x, kx dx. K you take outside, x square by 2, 0 to x, half k x square. This is work done by external force. Wext is this. But what is the work done by spring force? Work done by spring will be what? Because you are working against the force. So if you use this thing that F dr, you have compressed this one by x. I did not show compression here. Compression is x. Compression equal to x. Work done by spring will be what? This is force is in a direction opposite to displacement. You have given displacement this way, but force is opposite. So it will be minus kx dx integration from 0 to x. This is going to be minus kx square by 2. Okay? What happened in case of gravity? That I am going to discuss with you now in another problem. For work done in case of gravity, calculate work done to lift an object of mass 0.4 kg upward by a displacement or distance, upward I told, vertically upward 2 meter. Calculate work done to lift an object of mass 0.4 kg upward by distance 2 meter. Question is, who is doing work here? To lift the object upward, some external agent has to be there, isn't it? The external agent only will move it. This distance, this force is applied by external agent, F external. This has distance 2 meter and mass is 0.4 kg. So work done will be what? What is the force here? Force, if as you are doing the experiment very close to Earth's surface, then G will remain the same. What is the force here? Force will be m into G. That is force of gravity. That is m means 0.4, G you take 10, that is 4 Newton. So work done by external agent is going to be that 4 Newton into 2, that is 8 joules. 8 joule work done by external agent, but gravity acting vertically downward, mg. You have applied equal force upward, it's fine. What is work done by gravity now? Work done by gravity, don't say nothing, external agent is done. You have moved the body upward against gravity. So that you have to take into consideration. It will be minus 4 into 2 minus 8 joules. Work done by gravity minus 8 joule. Work done by external agent is 8 joule. Am I clear? Let us take another example here on the inclined plane. On the inclined plane, this is an inclined plane. Assume everything is uniform here. For this sum, remember the object is being moved slowly. Okay, there is no change of kinetic energy. Just work done by external agent. When you are doing, object is pulled, lifted upward slowly. Gravity also, gravity taking it downward by an acceleration g, that we cannot deny. So work done by gravity negative. Now consider this example. Find the work done if the object goes from A to B. Object goes from A to B. What does it mean? Who took the object from A to B? Is there any force? Have we applied any external force? No, we have not applied any external force. So object is going under the action of gravity. Isn't it? Object is going under the action of gravity. What force acts when an object is placed on the inclined plane? That force of gravity we have studied before in 4th chapter. That force is nothing but mg sin theta. Okay? So gravity will take it along AB. So work done by gravity, will be mg sin theta, the force, into displacement is along, force is along the displacement AB. Cos theta will be what? It is cos 0 degree. So this is nothing but mg into AB sin theta. But in this figure, what do you observe? H by AB equal to sin theta. So H equal to AB sin theta. Okay? Work done by gravity is mg into AB sin theta, that is mgh. So this H stands for what? Vertical height of the point. One very interesting fact we will be observing here, that if we have taken different inclined plane here, instead of theta I am taking here. In that case also, if we have taken it this manner, I am just drawing one inclined plane. This angle is theta 1. Obviously this point is something like AB dashed. In this case work done will be what? Here if you calculate work done, W will be the same manner. Force is acting down the incline is mg sin theta 1. Mg sin theta 1 into the displacement AB dashed. Now H is again AB dashed, so mgh. Work done is independent of path joining A and B. This observation also you can make here. This concept is required in future, that's what I am telling you. So work done by gravity here, you can write a note here, work done by gravity, work done gravity is independent of the path. It depends on the vertical height only. It's very important concept, should remember. So work done by gravity is independent of the path. It depends on the vertical height only. Now, a question arises, somebody has taken the object from B to A. What is going to happen? What will be the work done by gravity in that case? And work done by external force? Just as per our discussion that we can write here easily. Work done by an external agent to move the object from B to A, will be the same expression mgh. Why? Because in this case, if you discuss this one as a separate problem, in this case the external agent is taking from A to B the object of mass m, this angle theta, this is h. No, is taking from B to A as per our discussion. It will be from B to A. So this time to pull it upward, that pulling force going to be what? P is going to be mg sin theta. At any position, gravity will remain the same here, no? Small height gravity doesn't change. So force acting down the incline is mg sin theta. Pulling force has to be mg sin theta. So work done will be what? Work done will be P into AB, that is mg sin theta into AB. AB sin theta we have seen mgh. It is mgh. mg into vertical height. Work done by external agent. That is, external agent has done, I am writing W. W gravity will be what in that case? Gravity, you are taking against gravity, no? So work done will be minus mgh. Should remember this. External agent doing positive work, gravity is doing negative work, minus mgh. So in this example, mass is given 6 kg, AB equal to 4 meter, theta 30 degree. Find the work done by the pulling force of gravity. One very important thing you should remember, one condition, one statement will remain hidden. The object is being moved slowly. The object is being moved slowly. If there is change of velocity related problem, it must be mentioned over there. Okay? But it is not given, so we'll assume that object is being moved slowly. Now the next question is, what are the forces acting on the object? That you know, that mg cos 30 this manner, this is mg, I wrote wrong. This is just mg, vertically downward. Mg cos 30 will be acting this way. Fourth chapter, lots of sums were there. You have seen that, so I am not going to explain that. And you are moving the object slowly. So doesn't this imply that pulling force will be, without acceleration you are moving, pulling force P must be equal to mg sin theta, that is 6 10 sin 30. So this is going to be 60 into half, that is 30 only. So pulling force P equal to 30 Newton. Work done by pulling force, length of AB given. So first case, work done will be what? Work done will be that 30 is constant, not moving with acceleration. This multiplied by 6 joules. Newton meter. I did not write cos 0 degree here. You can write, but here P is mg sin theta and displacement along the force. So it is 180 joule. What is the work done by the force of gravity? Second part. This will be, this is work done by pulling force or external force. Work done by gravity. This is going to be minus 180 joules. So this you must remember. External agent doing positive work, gravity is doing negative work. In our following discussion, this concept will be repeated to get some other concept. Okay? Now let us go for another sum. Force acting on a particle is given by F equal to A plus Bx. Find the work done in displacing it from x1 to x2. This is variable force. So for the problems I have discussed with you, those are of constant value. But here it is variable value. So you write the expression for dw first. This is one-dimensional motion. X given means along x-axis only. Okay, this is example of one-dimensional motion. So work done going to be what? You find dw in displacing from x1 to x2. This is origin to x1 to x2. Okay? There is no issue if you have taken from x2 to, x1 here, x2 here. Similar. So dw will be what? Force you applied along x-axis only, F. So it is A plus Bx. Give a small displacement, dx cos 0 degree. By formula we know dw equal to F, dr will not be there, it will be dx only, cos 0 degree. So if you have written, dx you have written. So this is A plus Bx into dx. W will be x1 to x2 A plus Bx dx. If you integrate this, A into dx B into x dx from x1 to x2. Ax okay. So W going to be what? A into x2 minus x1 plus b by 2 x2 square minus x1 square. It's clear? Now in one problem I am going to include the concept of work done against friction or by the friction. Okay? Box of mass 10 kg is pushed up an incline of length 8 meter by 10 meter. No, 8 meter is enough because inclination I have told. 8 meter by applying a tangential force of 300 Newton. Intentionally I have used this term here, that component. Tangential force means component along the direction of motion. 300 Newton. Angle of incline 30 degree, mu given work done by the force of friction. See? External force acting, question is on force of friction. So you have to do it carefully, take the inclined plane. Angle of inclination 30 degree, length of incline given 8 meter. Take an arbitrary position of the object. Force mg acting downward. This way it will be mg sin 30 mg cos 30, and this is normal reaction. Okay? You are simply pulling it upward. By what force? By the force which is given by 300 Newton. Okay? Now, will this 300 Newton matter? Does it have any, you have applied the force, that 300 Newton, but does it matter? 300 Newton will not matter because you are going to calculate the force of friction, work done by the force of friction. You have applied the force, external force 300 Newton, if work done is required, you do it. No issue. But they have asked you to calculate work done by the force of friction. Okay? The object taken from A to B. Force of friction is what and in what direction it acts. Force of friction, Fr will be mu into N. Mu is 1 by root 3 and 10 cos 30 is root 3 by 2. We will be taking this into consideration, that is 50 Newton. This is the force of friction. So, force of friction is acting downward, isn't it? Because pulling force upward. Pulling force work done not required. If it is required, then it will be simply 300 into 8. But here, this one is work done by force of friction. Displacement opposite to force, the work done has to be negative. Wfr will be what? That if Fr multiplied by the distance multiplied by cos 180. Why? Because force of friction downward, it is moving upward. So angle between them 180 degree. If Fr 50 and length 8, so this work is minus 400 Newton. Clear? Don't forget the sign here. Don't forget the concept here. Okay? We can do difficult sums on friction in another session. Work energy power related to friction. But here, I am going to explain how to calculate now at present, how to calculate work done by using graphs. Graphically, work done by constant force, this is graphically. We are going to find graphically how to find work done by a constant force, and this force is one dimensional. Two or more dimensional, two or three dimensional, I will be discussing definitely, but let us understand this part first. Work done by a constant force. Force remain constant and it is one dimensional. Assume that it is acting along x-axis. Okay? Along y-axis. Force along y-axis, displacement along x-axis. This by definition W will be what? Same direction, fx cos 0 degree. That is simply f into x. A force F is there and you have given a displacement d or x, whatever. This is your force applied. So work done equal to what? F into x. But work done F into x in this diagram, don't you think that it represents the area of rectangle? This is equal to area of the rectangle. Work done equal to F into x. This is equal to the area of the rectangle. So this is graphical representation of work done. W equal to F into x. We have done it one dimensional constant force. If it is one dimensional variable force, if the force is variable, it is changing, it will not remain the same. With time, with displacement, the value of this force going to be changed. How do you account for the work done? This is your F, this is x, force this time is a variable. Just take it this manner, force is a variable. How do you account for work done in this case? A to B. Force is changing, it goes to some maximum value, then it is decreasing. This time I will be using the concept of integration as well as the graphical presentation. We are doing it graphically, that for constant force what we have done. So imagine that the displacement, whole displacement from A to B, that is definitely along x-axis, AL and BM, that is along x-axis. So this whole path force is not constant, it is changing this manner. Just I show you here. Suppose for this part force is F1, for next part force is F2, F3, Fn, this manner. I will be taking a force F for this part and the particle is given a small displacement dx. Okay, this dx is very small, f into dx or delta x, whatever you have taken, it is very small. this displacement given along x-axis be delta x. Okay, this may be f3, f4, whatever, it is representative of all. That's why I have taken the general expression. So what you are doing there, this interval x you are dividing into small parts, each of length delta x. Then work done by f1 you calculate, f1 delta x, f2 delta x, this plus fn into delta x. Now, if we use the summation sign, this is going to be sigma f into delta x, summing over the whole interval. This is all coming f into delta x. If you say that it will be delta x1, delta x2, no problem, you can take it that way also. But all these can be expressed in terms of summation. If you take delta x1 here, delta x2 here, delta xn here, then this is fi delta xi, I equal to 1 to n. That I have taken as sigma f into delta x. Okay, this is work done by all the forces, work by resultant force. I mean, not resultant force, work done by the force F, which has values F1, F2, Fn this way. Maybe external, maybe internal. Now, if delta x tending to 0, then work done going to be what? If delta x tending to 0, then work done will be integration f into dx, assuming that delta x is very small, it is dx. I will say that this thing is also area under the curve. Area under the curve means that fx curve. Why? Question arises why? Its origin actually integral calculus. This f into dx, you will say that f you have not mentioned whether at the point P or at the point Q. If delta x is large, there is no problem. Then you then you divide that f into again smaller parts, do it. But we have taken delta x tending to 0. Delta x tending to 0 means this is very small. For very small, the area of the inner rectangle, if you take this one as Rs, and the outer rectangle, there is no difference between the curve, the area bounded by the curve, or by the inner rectangle PLRS, or by the outer rectangle. So that's why this, when you take delta x very small, this part represents area under the curve for this portion. Previously, area under the curve for this portion. Previously, area under the curve for this portion, as you have taken all those segments very small. So don't you think that by adding all these areas above x-axis, I'll get the area bounded by the curve with the x-axis. That's why I've written W equal to f into dx, area under the curve. Let us apply it in solving a very interesting problem. So for this example, force is changing from O to A, 200 Newton maximum, variable force. But here it is constant. And below, negative. I mean, opposite to direction of displacement. How to calculate work done in this case? So we'll be using, for constant force we know it is area, for variable force also we know area. So work done in this case, work done going to be area of this portion. Take this point as M, this one N, this one RS. Work done equal to area of this curve O2A with x-axis, area of OAM minus area of MRSN. Area of OAM will be what? Half into 6 into 200. MRSN area will be what? 150 into 3. Hope you have understood. So this is going to be 600 minus 450 joules. So this is going to be 150 joules. Work done equal to 150 joules. Clear? So this work done is positive finally. Situation may be there as follows, where force acting on the object is not one dimensional, maybe two dimensional, maybe three dimensional, and the particle is taken along the curve like this from A to B. How to calculate work done in that case? In this diagram, the forces acting on the particle are taken as F1, F2, F3, Fn this manner. Those forces making angle theta 1 with horizontal, this F2, theta 2, F3, theta 3, and this is theta n. And we have assumed that F1 is responsible to displace the particle or the object by delta S1, F2 by delta S2, F2 moves it by delta S2, and Fn, force is variable, it moves by delta Sn. Okay? How to calculate work done in this case? We remember the concept that work done will be force into displacement. So what do we need? We need the component along x-axis. If we want to calculate, if we express everything in terms of x coordinate, then only graphically I can show you, no? Because this force is acting in 2 or 3 dimensional, I told you. Displacement also accordingly. But finally, I want to calculate the work done to displace the body from A to B. Expression I am going to derive in terms of displacement along x-axis, and then will generalize like in 3D. What will happen? Let us link with the concept we have already learned. Along x-axis, area will be there for work done, and secondly, that area will be total area, that work done will be total area bounded by the curve with the x-axis. So we are assuming that it goes from A to B. Along x-axis, it is from M to N. Certain x coordinate x1 to x2 say. So to calculate that work done, WAB, okay, you first write W in this form. If it is not small enough, we cannot write that, no? That W will be equal to another thing, that F1's component F1 cos theta 1 will take the particle along x-axis. This one will be f2 cos theta 2. This one will be sorry, fn cos theta. So W is going to be AB if we write it here only, that f1 cos theta 1 into delta S1, f2 cos theta 2 into delta S2, fn cos theta n into delta Sn. Again, by using the sigma sign, this is going to be sigma f cos theta into delta S. Again, if you imagine delta S tending to 0, then WA to B will be what? Integration A to B f cos theta into ds. This is A to B f dot ds. Okay, and this is equal to area bounded by the curve, because the same concept. F1, what work does it do here? That is area. F2, what work does it do here? F2 into area. That is area with the x-axis. If you add all the areas, then it will be area bounded by the curve. Which curve? Fs curve. This we have taken S or X, whatever, by the curve with x-axis. Clear? Hope you have understood. So, car developing 6 kilowatt of power while moving with a velocity 54 km per hour on a level load. Find the force of friction. We need to remember power formula. P, we have seen that F dot V. Okay? P is equal to F dot V. This velocity 54 km per hour on a level load. So obviously theta going to be 0 degree, same direction, and velocity will be 54 into 5 by 18 meter per second, that is 15 meter per second. They have given that power developed is 6 into 10 to the power 3 watt. This is the power developed. So here the expression we write P equal to Fv cos 0 degree. This force we have to find the force of friction. It is car moving with the velocity. What force is effective over there on the road? Without friction, car cannot move. So power is developed, work is done, and power developed. Power is developed here by the car, because it is working against the force of friction. So find that force. F into V is 15. So F going to be this divided by 15. 6000 by 15, that is 400 Newton. Okay. Man moves up a hill whose slope is 1 in 10 with a velocity 12.8 km per hour. Weight of the man is 80 kg. Find work per minute and the power developed. I have to make this thing clear. What is 1 in 10? Okay. 1 in 10 means the vertical height is 1 and length of the incline is 10, something like that. So that you can easily write sin theta equal to 1 by 10. Whenever given this manner, whose slope is 1 in 10, you will say that slope means tan theta. Okay, but theta small means you can replace tan theta by sin theta also. So sin theta 1 by 10 here. Velocity is 12.8 5 by 18 meter per second. We need this unit to calculate work done per minute and then the power developed. Weight of the man is given 80 kg. So for the man whose weight 80 kg, he himself is working, no external agent. Man is the external agent only. Okay, man is doing work. So that force, he is working with the force which act in, this is not work done by gravity, work done by man. So this is mg, this one mg sin theta, this one mg cos theta, and man is moving up the incline where the force equals with mg sin theta. So force applied will be mg sin theta. Mg sin theta means that is 80, 10, 1 by 10. So 80 Newton. Clear? This force is 80 Newton. Then work per minute. Work per minute. First find the work done. Work done, how to find here? So instead of calculating the work done by the formula F into S cos theta, we write work done by alternate formula. That will be what? Work done equal to, that is F into S you know, power is F into V also you know. Here V is known. Power developed we have to find. Power developed will be, we need this also, no? V also, F also required. So we have to put it there. Power equal to F into V. It is along the direction of velocity. So there will be 80 multiplied by 12.8, 5 by 18 along the incline. So cos 0 degree is there. So now simplify it. There it will be, cancel a factor. What factor? 80, 12.8 into 5. That divided by 80. Let me calculate. 285 joule. Okay? No, joule per second. Per minute how much? So work per minute. Work per minute will be F into S divided by 60 you put there. Because 1 minute is 60 seconds. F into S you have to calculate. But where to get the value of F? Here in this problem, so we will not use any formula on work done here. Work done, for calculation of work done per minute, this is this is joule per second. So work done in 60 seconds going to be 285 multiplied by 60. this much joule I am getting. So before we end this session on elementary idea of work, energy and power, don't say all the kind of energy, just kinetic energy. We will be doing few more on kinetic energy. We have seen that kinetic energy at B minus kinetic energy at A is equal to work done to take the particle from A to B. F dot dr, or you write A to B F dr cos theta. For constant force, you take F outside, and that for constant force you can easily prove that this is actually kinetic energy at B minus kinetic energy at A. How to? Let me start with this simple example where to prove it for constant force. For a constant force, F acting on the particle of mass m to take it from A to B, here velocity is Va and here velocity is Vb. So force is responsible. We can imagine that there is a acceleration or deceleration, but calculation will not matter. So work done will be change of kinetic energy. If the force acting this manner, we assume that the force will increase the kinetic energy. So work done, this distance you have taken from A to B, S. Then if Vb greater than Va, the force must have acted along the direction of displacement, and work done in this case, calculation will be by finding the force acting on the particle. In going through this distance, velocity changes from A to B. So Vb square equal to Va square plus 2As. A going to be what? Vb square minus Va square by 2S. So force acted on the particle is how much? Force acted will be F equal to m into A. That is m into Vb square minus Va square by 2S. Okay, so work done is what? Force acted along the direction of displacement, it will be Fs cos 0 degree. Nothing but m Vb square minus Va square by 2S into S. Half m Vb square minus half m Va square. So this is kinetic energy at B minus kinetic energy at A. It's done for constant force. Now for variable force, how to prove this thing? Work done by variable force, and this work done, as you have seen that change of kinetic energy also area under the curve. We have seen this already. Area for variable force. Let a variable force F act on a body to displace it by distance dx. Small work done will be what? dw f dx, f into dx. Imagine that displacement is along the force direction of force applied. So net work done to take the object from A to B is given by W A to B equal to integration of f dx, A to B. This is nothing but A to B. F is what? F is mass into acceleration. This you write m into dv by dt into dx, but time will not keep there. So this will be A to B m, you write this thing as dv by dx into dx by dt. Okay, force is m dv by dt, that into dx, but dv by dt is what? dv by dx, dx by dt into dx. Clear? Check once. dv by dx, dx by dt, this multiplied by dx by dt. So dx get cancelled. There it will be mv m into, no, don't cancel, you write m into v dv by dx into dx, because since v equal to dx by dt, dx get cancelled, it will be A to B mv dv. So W A to B for variable force is A to B mv dv. Take m outside since this one is constant. V integration v square by 2 A to B. So it will be half mv v square minus half mv square. This is Kb, kinetic energy at B, minus kinetic energy at A. Okay? So, work is done on a body via force, and that force is responsible for changing the kinetic energy of the object. Am I clear? There is a beautiful application, concept application on this. So, for this problem, object of mass 2 kg is subjected to a force as shown in figure. From A to B, the force changing 2 Newton to 3 Newton. Initial velocity of the particle given 1 meter per second. Your problem is to find the gain of kinetic energy as it reaches the point B, final speed at B. So this is actually application of all the concepts you have learned today. That area under the curve, fx curve, is the work done. Work done is change of k, that is final k minus initial k. So let us do it here. It goes from A to B. In going from A to B, in going from A to B, can you calculate the work done? Work done will be area of this portion, just this one. Because particle is not going from O, it is going from A. So half into 5 into this 5 is here. Tale, in this case, in going from A to B, work done will be half into 5. I mean, you just take its sum of two parallel sides into distance between them. So that is going to be half of 2 plus 3. this side OA is OA, that area of trapezium. OA is 2 Newton plus 3 Newton. This multiplied by distance between them 10. This is nothing but 5 into 5. 25 Joule. Gain in kinetic energy you got, it is 25 Joule. Now the problem is mass of the particle given, you have to find the velocity at B. First part is done here. For second part what to do? Now work done equal to half m Vb square minus half m Vs square. Velocity at A given 1 meter per second. So 25 equal to half into mass 2 kg Vb square minus 1 square. So these two get cancelled. Vb square 26. So velocity at B will be under root 26 meter per second. Okay. When you do it with me, it is very easy to do it. Now, when you are solving problem, it may include, variable force in space, then how to tackle those kind of problems, I will not be discussing today. Hope till what we have done today is clear to you. Okay, next session will be coming with the concept of potential energy, conservative and non-conservative forces. Very interesting session ahead.